Hello and welcome back to another video with It's Dr. Dan, and today we're going to be looking at part 3 of our 4-part series on intermolecular forces, which I know there's a lot of videos on intermolecular forces, but the big thing is that it's extremely important for understanding it for general chemistry and how we can really understand how molecules behave. So before we talked about dispersion, which was our weakest force of attraction, which is something that we find in all molecules, which is really important to realize that everything can do it, but it's something that has a big impact in terms of the size. But when it comes to polarity and having a dipole, this has a bigger effect. So in this video, we're going to focus on dipole-dipole, what they are, hydrogen bonding, describe that as well, and ion-dipole. So we're going to look a little bit more in detail. Then we're going to be comparing them and trying to understand, all right, well, what kind of force do they all have? And then we will take a look at what properties these all affect for our final fourth part of the series. Okay. So let's take a look at this to understand it. Okay, so dipole-dipole forces are referred to as the stickiness that holds together different polar molecules. So really what this is when you have a dipole moment that is there, it means it's a permanent dipole. So it's always a little partially positive, a little partially negative. It's not the same thing as ionic, which has a complete positive and minus. They're a little different. So when you have something like HCl, the electronegativity difference between the two will cause them to interact with, let's say, another HCl molecule. So if they are to try to come in contact with one another, the positive is going to interact with the negative. So if you were wondering, like, okay, well, how would they approach one another? Well, the negative part is going to come in contact with the positive, and then they're going to be attracted to one another to actually show, all right, well, we have this temporary force, or that we have this force of attraction that's happening to make this dipole-dipole characteristic. And this is something that could affect like the melting point, the boiling point, the viscosity, all these other little concepts as well. Now, dipole-dipole isn't the only form of force that's polar, right? So there's also hydrogen bonding and ion dipole as well. Each of these are increasing levels of strength as we are looking at them. Okay, so the next one, which is looking at, okay, we have hydrogen, we have dipole-dipole, which has that dipole force, is hydrogen bonding. So what is hydrogen bonding all about? Well, essentially, this is going to be considered a special type of dipole-dipole force. So it's very common for different teachers to say, okay, this falls under dipole-dipole, but it has its own special definition. It's something that's like dipole-dipole is like stronger, bigger brother, is someone that's a lot tougher. So one thing that we generally try to look at here is that you need a hydrogen atom, and it has to be bound to either a nitrogen, an oxygen, or a fluorine. It has to be one of those different atoms. The way I remember that is if you kind of look at these atoms here, so you have FNO. Remember FNO? You'll never forget it. So FNO, hydrogen bonding, you'll remember that these has this interaction here. So keep in mind though, even though this has the word bond in the name hydrogen bond, it is not a real bond. It's an interaction, okay? Electrons are not being transferred. It's an interaction between different species. So if we were to see these different examples here, we have water, right, which is oxygen and hydrogen. They can interact with one another and actually make a dipole or hydrogen bonding interaction. We can have ammonia with another ammonia. They can interact. You can have HF with another one, and all of them fit the definition what we consider a hydrogen bond to be, right? It has to have either nitrogen, oxygen, or fluorine in all these different examples that are here. Now, why is hydrogen bonding so important? Well, this is something that occurs in all kinds of different large compounds that we find in biological systems. So for all of you that are in health science and biology, you have to be able to label how the hydrogen bonding works, which essentially there's two definitions that we have. There's hydrogen bond acceptors and hydrogen bond donors. So acceptors are what we are seeing on essentially the right-hand side of our molecule over here, right? So we have our oxygen is accepting the hydrogen interaction, whereas the donor is the side with the hydrogen. Okay, so it's the part that has the NOF component on it. So keep in mind, a hydrogen bond does not need to be with the same element. It could be something that's different, right? So here I have O and O. That does not have to be the case. So if I were to ask you, okay, can water hydrogen bond to itself? And the answer is absolutely, right? I showed you that earlier, right? We had water talk to another water. They can interact with one another. What about ammonia and another ammonia? Can they do it as well? Well, once again, we have that FNO, right? Nitrogen is connected to a hydrogen. They can also interact. They can have that force of attraction. But what if I try something like trimethylamine? Can that one interact? Well, if I were to try to write that, can we have a hydrogen bond occur? Well, one thing that we can like zoom in here is you can see, well, I have a carbon bound to a hydrogen. Does that fit our definition? And then you can kind of think like, no, it doesn't, right? It needs to be fluorine, nitrogen, oxygen is what the hydrogen has to be connected to. And that's none of them. So remember, the hydrogen has to be connected directly to the nitrogen, oxygen, or fluorine. That's not happening here. So this is not that type of force. It could be a dipole-dipole force, but it cannot be a hydrogen bond. It needs to fit the definition. What about hydrogen gas? Can that hydrogen bond to itself? It is hydrogen, it's in its namesake. So could that happen? But if you think of H2, it's one of our 7 diatomics, right, that we learned about in previous videos. Is it polar or is it nonpolar? And being that they are all linear, they are nonpolar. So it's not, has to be polar. That's the other thing that's really important. It must be polar. So why are hydrogen bonds so freaking important? Why am I trying to spend so much time for you to understand this? Well, it's because if anything, it's something that even though it might only be 2% of the strength of a real bond, it's what's holding you together at the seams, right? So all of your genetic information, all of the DNA that's in your body, every single interaction that we have with all these different base pairs is something that's being held together with hydrogen bonds. So without those hydrogen bonds, your DNA would be susceptible to mutations, to different cancers, to viruses, all these things that could to completely change who you are. So all these are hydrogen bonds. It's what keeps them all safe, but put together. So that way, your genetic information is maintained and passed from the next to the next. So hydrogen bonds are really important. It's also what holds together all a lot of your protein structures, your enzymes. It's what helps keep all biological systems intact. So it's the most important interaction out of all of them. Now, what other important interaction is also ion-dipole forces? So in order for this to happen, what the Y is here, it needs to be a ionic compound mixed with a polar compound. This is typically where a term known as solubility comes from. So like dissolves like, trying to understand how homogeneous mixtures come apart. So if I put salt in water, well, the salt, Na plus and chlorine minus, is going to break apart and it's going to interact with the water molecules, allowing for water to surround it on all sides for it to dissolve. So this has to be an ionic compound dissolved in water or another polar liquid. Okay, let's take a look and try to understand, can we label all these different types so we can try to predict which one's going to be the strongest forces out of all of them and look at some different molecules. Okay, so when you're comparing molecules of similar size, meaning stuff that's usually about the same molar mass, you have to be able to rank and understand what is your strongest intermolecular forces. So here I have from weakest to strongest, right? Dispersion is your lowest, ion-dipole is the strongest. In most general chemistry and organic chemistry courses, you're typically looking at the first 3 when you're looking at properties, but ion-dipole does feed into solubility. So, for example, what do I mean by this? Well, when we're trying to understand the different sizes, we have to keep in mind that they all forces are most likely possible here. So let's say if I have water, it can do hydrogen bonding, but it can also technically do dipole-dipole and dispersion. HCl can do dipole-dipole and dispersion. So to kind of go back for a second, well, if water can do 3, 2, and 1, and HCl can do 2 and 1, well, the way that we can actually think of this in terms of an analogy is similar to how like subscription plans work for different companies and different things that you can buy online. So everybody does dispersion. This is as if you sign up, make an account on the website, you have access to all the basic functions of that website. However, there's always stuff behind a paywall. Everybody has to get paid somehow. So dipole is like your basic subscription. You have your base subscription. However, you still have access to all of your general materials. So if you have dipole, you also have dispersion as well. Hydrogen bonding is like your premier access. Instead of paying $5 a month for dipole, you're now paying $10 a month for hydrogen bonding package. Maybe you don't have ads on this one or something. Well, now that you're paying for this one, you also get what was in the dipole package, and you also have what was in the dispersion package as well. So you have the other tiers on top of that. But wait, there's more. You can also download potentially the VIP access to this subscription plan. You can pay a whopping $25 a month to get this one. But you still have access to hydrogen bonding, dipole, and dispersion down the line. So the way you can look at these forces in general chemistry is if you have access to the strongest force, you generally have access to the forces below it as well. Consider it like a subscription plan when you're trying to look at these. Not trying to sell you, I think, but I'm just telling you that's the easiest way to look at it. So if we were to look at this one here, so we have CH2Cl2. The easiest way to do these is being able to draw the Lewis structure and to represent it in the VSEPR geometry. You have to get efficient in writing. So if you want to pause this video and try to draw it yourself, I fully recommend that. So I'm going to show it for you. So if I were to represent that, right, I have CCl2, H2, right? And what we are going to do is you have to label, does it have dipoles? And one thing you're looking for is, well, it is tetrahedral, but does it have the same atoms on all sides? And you can say, well, no, it doesn't. So that means it's not symmetric. So it's not going to allow for only dispersion. So there is a dipole here. So it can interact with, let's say, another molecule, giving it access to dipole at the minimum. But keep in mind, that's your tier 1 of your subscription plan. So if you have that plan, you also have access to the basic membership as well. So if you can do dipole, you also can do dispersion as well. Okay, so you have both of those different forces that are available. Okay, so you have your basic membership and then premium access. So if we were to do another one, let's say if I wanted to mix methanol and ethanol, what is the dominant intermolecular force here? Well, ethanol and methanol are two organic compounds, which is for anyone that's in M3B for my courses. These are essentially things that have alcohol groups on it. And one thing that you'll see is that there's this OH component. If you see OH, NH, or FH, a bell should ring in your brain. And that's letting you know, ooh, these are actually capable of doing hydrogen bonding, right? We have this interaction here. Here's our hydrogen bonding definition. So what is our strongest force? Well, hydrogen bonding is your strongest. And is that all it can do? Well, that might be its strongest, but it also has access to dipole and dispersion because all those parts are possible. So anytime you see a molecule with an OH, think hydrogen bonding. That's going to be your most important part of this individual of these molecules. So now what makes this so important? Well, when you have these polar molecules that are interacting with other polar molecules, This is where that phrase, like dissolves like, is extremely important to understand. Polar molecules dissolve other polar, nonpolar dissolve nonpolar. So if you have things that are both dipole-dipole, both hydrogen bonding, both ion-dipole, or a mixture of those, they will dissolve one another. If it is only capable of dispersion forces, then those will dissolve to other only dispersion. If they are a mixture of the same two, typically they're referred to as immiscible or insoluble because they cannot be mixed together. All right. So if I were to ask you, all right, well, can, let's say, methane, CH4, dissolve in water? Well, CH4 is tetrahedral. It's all the same atom, meaning it's symmetrical. So it's nonpolar. It's dispersion. Water can do hydrogen bonding, so they can't dissolve. But let's say if I change one atom, let's say I put a fluorine on it. Fluorine is your most electronegative element. So now what do we have? We have a dipole. Can something with a dipole dissolve in water? Well, if you remember, like dissolves like. So the answer is yes, it can. Now it's possible. So the power of substituting one element can make this possible when we are trying to look at all these different little things. Or is it possible to dissolve? So if we were to try to look at some of these other ones and try to understand, like, well, all right, well, can they possibly dissolve one another? Can we understand them? Well, it all comes down to trying to understand your forces. The first thing you need to do is write your geometry, draw the structure, and see what forces are possible. So that way you can try to rank them, understand what exactly are they capable of when you're looking at these different structures. And that can sometimes be the hardest part. So thank you so much for listening to this part. I hope that this video helped you understand a little bit more of the details behind it. We're in our next part of our video, our last part of the hydrogen bonding series. We're going to try to understand what other properties can be affected by nuclear forces. Thank you so much for listening.